Okay, so when we last left off, just as a recap, we discussed radical stability last session. Now we're going to be discussing carbocation stability. Carbocations are electron deficient species, and as a result, they're stabilized by adjacent bonded atoms. So as we move from primary to secondary to tertiary, our carbocation stability increases. Okay, so the tertiary carbocation is our most stable carbocation. Now, to help explain as to why are carbocations stabilized by adjacent atoms, again, we'll invoke this idea of hyperconjugation. So in hyperconjugation, we have the overlap of a p orbital with an adjacent sigma bonding molecular orbital. So adjacent to our carbocation, we have these sigma bonding MOs. So we have these sigma bonds adjacent to our carbocation. And each time when our sigma bonding MO, so our sigma bonding MO is adjacent and aligned with our p orbital, we can end up with a weak overlap. And this weak overlap stabilizes our carbocation via donation of electron density. So we're donating some electron density from our sigma bonding molecular orbital into our electron deficient p orbital. So the more sigma bonds we have adjacent to our carbocation, the greater the stabilizing effects. That's why the tertiary carbocation is most stable, because we have the most number of adjacent sigma bonding MOs to participate in hyperconjugation. Very similar to what we've seen for radicals when we discussed hyperconjugation with respect to radicals. Okay. So to draw out a detailed picture, if we're looking at the ethyl cation, which looks a little bit like this, we can draw this as CH3, CH2 plus. And now let's look at it from an orbital picture perspective. Let's look at it from an orbital picture perspective. So we have our sigma bond between our carbon sp2 and hydrogen 1s. We have a sigma bond between a carbon sp2 and a hydrogen 1s. We have a sigma bond between a carbon sp3 and a carbon sp2. Okay, and now let's get to the real meat of our discussion here. We have our p orbital. Now, suppose when we look at one of our carbon hydrogen bonds, so if we look at one of our carbon hydrogen bonds, so this is a sigma carbon sp3 plus hydrogen 1s. When this sigma bond is aligned with our p orbital, we can end up with an overlap. And this overlap between our sigma bonding molecular orbital and our empty p orbital is described as hyperconjugation. And in effect, what we're doing with hyperconjugation is we're taking some of this positive electron deficient character that is on our ethyl cation carbon, and we are distributing it throughout our molecule. Analogous in concept to how resonance can distribute a charge and distribute electron density throughout a molecule. Now, the key feature I want you to pay attention to is the fact that this carbon-carbon bond can rotate. So each of our carbon-hydrogen sigma bonding molecular orbitals has a chance to participate in hyperconjugation. Now, hyperconjugation and sort of the strength of this stabilizing effect does depend on the exact nature of the sigma bond. But for the purposes of this class, we're mainly looking at this carbocation is stabilized by this adjacent methyl group. And the more adjacent alkyl groups we have, the more we can stabilize our carbocation via hyperconjugation. Does everyone understand from an orbital picture perspective how hyperconjugation functions? It's an overlap of our sigma bonding MO and a p orbital that stabilizes our p orbital via donation of electron density. This is not a very strong overlap, but it has a significant effect on carbocation stability. Does that make sense to everyone? Anyone have any questions so far on this idea of hyperconjugation? Okay, so one thing I want you to keep in mind, the hyperconjugated carbon-carbon sigma bond, so this sigma bond right here, so this carbon-carbon sigma bond, we have direct sharing of electron density along the bond axis and also above the bond axis via hyperconjugation. And since the carbon-carbon bond is rotatable, each of the carbon-hydrogen sigma bonds can participate in hyperconjugation, as we've seen above. Okay? In effect, we've delocalized our positive charge over a total of 4 atoms, where we have our carbocation carbon, as well as each of the atoms participating in hyperconjugation. So just like resonance can distribute charge and electron density throughout your molecule, through hyperconjugation, we've in effect delocalized and stabilized our carbocation charge. Now, it's not just carbon-hydrogen bonds. Carbon-carbon and other sigma bonds can also be involved in hyperconjugation. As long as you're able to overlap with the p orbital, you can stabilize your carbocation or radical via hyperconjugation. Okay, so this looks a little bit like review from our discussion of radicals. So let's keep going and let's talk about resonance effects. So carbocations are stabilized by adjacent pi systems, as the cation can be delocalized via resonance. And we saw this before in chapter 2 when we started drawing resonance forms and saying, what is the most stable cation? What is the most stable anion? And essentially the reason why resonance is so stabilizing is that we're distributing our positive charge over multiple carbons. And since when we distribute the charge over multiple atoms, we minimize the positive charge that is experienced by any single atom. So for example, your conjugated carbocations are more stable than your unconjugated carbocations. So we call these carbocations allylic carbocations if they're adjacent to an alkene. If they're adjacent to an aryl ring or a phenyl ring, we call these benzylic. This is why allylic and benzylic carbocations are especially stable. One thing I do want you to note, this effect is additive. So the more atoms you can delocalize a charge over, the more stable your carbocation is. So the more atoms you can distribute your charge over, the more stable your carbocation will be. This looks pretty familiar, right? Let's start to add some additional ideas and talk about some substituent effects. So resonance donors, everyone remember this term? It's the idea of atoms that can donate electrons via resonance. They stabilize carbocations by donating electron density into the empty carbocation p orbital. Okay, so if we compare carbon to nitrogen, what is the key feature of nitrogen? What distinguishes nitrogen from carbon? What does nitrogen have that carbon does not? A lone pair to donate, exactly right. So we can kick that lone pair down and we can distribute our electron density over multiple atoms. Now, what's really cool is halides also stabilize adjacent carbocations. So you think a halide, for example, is electron withdrawing. It's an electron withdrawing group, but it's also a resonance donor. And in general, resonance effects will win out over inductive effects. So we can just as easily kick our chloride electrons down and stabilize our carbocation. So I always want you to keep in mind resonance effects have a pretty strong stabilizing effect on carbocations, and they even beat out inductive effects, right? Nitrogen's electron withdrawing, oxygen's electron withdrawing, but their resonance effects are far more important because via resonance, we're taking this positive charge and now spreading it out over multiple atoms. So here's some examples of arrow pushing for resonance that I've drawn on the side up here and down here for your reference. And the key thing I want you to keep in mind, the resonance effects are stronger typically than inductive effects. With just a little star next to it, just in this case. Does this idea make sense? Does this idea of resonance stabilization make sense? Is everyone comfortable so far? Okay, perfect. So let's keep moving then. And let's talk about carbocations and inductive effects. So inductive effects, carbocations, since they're electron deficient, just like radicals, which are electron deficient, they are destabilized by electron withdrawing substituents. So examples of electron withdrawing groups are ketones, carboxylic acids, nitro groups, nitrile groups, and one thing that I want to just make as a side table is electron withdrawing groups by resonance, and these are super destabilizing to a carbocation. These are your nitro groups, your ketones and aldehydes, and your carboxylic acid. And the reason why these groups are especially destabilizing is they're not only inductively withdrawing, but they also pull electron density towards them via resonance, and they can easily delocalize electron density via resonance. Okay, so you don't want to have your carbocation adjacent to an electron withdrawing group. Okay, so there are two things you want to keep in mind. You want to make sure that the electron withdrawing group has an atom that's more electronegative than carbon. And you want to make sure the atom directly attached to the carbocation does not have a lone pair. Otherwise, it can participate in resonance donation. You can think of this idea, and the reason why electron withdrawing groups are so destabilizing is that we have these two adjacent carbons, both with a formal positive or partial positive charge, and we do not like to have like charges adjacent to each other. The other way that I think about it is that if you try to further draw, if you have an electron withdrawing group adjacent to the carbocation, you're further destabilizing your carbocation by further pulling away electron density from that carbocation. Now, the reason why you don't observe significant resonance effects in this case is because if you try to draw a reasonable resonance structure that places electron density on our carbocation, you often end up making an even more electron deficient atom, or that resonance structure will be minor. Do these electron withdrawing groups look familiar? Is everyone comfortable with this idea that electron withdrawing groups destabilize our carbocations? Any questions on this idea? Okay, let's keep moving on then. Let's talk about orbital effects. So carbocations are electron deficient species, and they're destabilized the closer they are to the nucleus. Again, this sounds a lot like our discussion of radicals, since both are electron deficient species. So increasing S character results in a shorter orbital that is closer to the nucleus, which, as we've established, the nucleus is positively charged. This, in turn, destabilizes our electron deficient carbocation. So as we move from an sp3 to an sp2 to an sp hybridized atom, our carbocations are most stable when we have the least S character. The farther away your orbitals are from the nucleus, the more P character your orbital has, the more stable your carbocation. The more S character you have, the less stable your carbocation is. This is the exact opposite effect observed for anions. Does this orbital effect discussion make sense to everyone? Does anyone have any questions on this idea? Okay, let's keep going then. And don't be shy to stop me, unmute, and ask a question. To test that we really understand what's going on here, let's try to indicate the more stable carbocation in each case. So going back to your the example for hybridization, the instability, the reason why an sp carbocation is unstable is it's being held closer to the nucleus, which is positively charged. And we don't like to bring our like charges adjacent to each other. In general, carbocations want to be in an orbital that's as far from the nucleus as possible. So the most possible P character. Does that make sense? So yes, you can think about it in terms of charge. Yep. So let's take a look at the following pair, and we'll have the left be A, the right be B. And I'd like you to take a moment and I'd like you to type in chat, what do you think is the most stable carbocation in each case, A or B? And look at the structures really carefully and check how many atoms are participating in resonance. So I see a lot of people typing A, that's correct. So we have benzylic. And I count 1, 2, 3, 4, 5, 6, 7 atoms that can participate in resonance versus this allylic carbocation where we have 1, 2, 3. So the more atoms we can delocalize our carbocation charge over, the more stable our carbocation will be. Okay, let's try this next example, A or B for this second block. So which one is more stable? Which carbocation is more stable, A or B? And don't be shy to type in the chat. I see a lot of people typing A. So if we look at adjacent atoms, this oxygen is a resonance donor. So we can just as easily delocalize our charge to stabilize our carbocation. So we're 100% correct that A is more stable. Okay, let's keep going now. Let's compare A versus B, and I'd like you to take a moment and tell me which carbocation is more stable, A or B. See a lot of people typing B. That's exactly right. This nitro group is inductive withdrawing, and you want to have the farthest distance from your inductive and resonance withdrawing groups as possible. Exactly right. Everyone's doing great at this. Okay, let's take a moment and let's look at our last pair of compounds. So A versus B. And this is an important problem because we'll see this type of carbocation rearrangement later on in this chapter. So which species is lower in energy, A or B? And just to help spark everyone's, so this carbocation is secondary, this carbocation is tertiary. So take a moment and type in chat which carbocation you think is lower in energy. So I see a lot of people typing B now. That's exactly right. Carbocations are stabilized by increasing substitution and increased adjacent sigma bonds. So the tertiary carbocation is more stable. Perfect. Any questions so far? Any questions so far on any of the examples? Is there anything I can clarify so far? If not, we're going to keep going. So let's look at this next batch. So we'll look at A, B, or C. And I'd like you to tell me what is the lowest. Oh, sorry. Yep. So for the last one, we're looking at carbocation substitution. This carbon is secondary. It has 1, 2 carbon substituents attached. The carbon on the right is tertiary. It has 3 substituents attached. So then, if we draw out all the hydrogens, we can see very clearly that carbocation B will be more stabilized by hyperconjugation versus carbocation A, just because there are more adjacent sigma bonds that can overlap with our carbocation p orbital. In general, carbocations are more stable with increasing substitution. Does that make sense? Perfect. So let's take a look at this next batch to round off our summary of carbocation stability. And let's take a look at A, B, and C. And I'd like you to tell me what the lowest energy carbocation will be. A, B, or C? A, that's exactly right. That's exactly right. It has to do with the fact that from hybridization, we want to place our carbocation in an orbital, or more specifically, we want our carbon atom to be hybridized in a way that we have the least amount of S character. We want our orbitals to be as far as possible from the nucleus. Okay, now this last one is pretty interesting. So if we compare A and B, so let's take a moment. Let's think over this problem. Let's think over and think about this problem a little bit. And I'd like you to tell me which of these carbocations is more stable. And for this, I would encourage you to build a model kit. So this really brings up this idea of strain and geometric strain. And so just take a moment and try to build a model and try to think just in terms of, hybridization in geometry, what the geometry would look like at this vinyl cation. So this one I'd like you to take about 1 to 2 minutes to work on, and I'd like you to really consider what's going on here. So try to tell me what the lowest energy species is and try to explain why it's lower in energy. And I encourage you to build a model of this system. And really try to think about the hybridization of this carbon, this carbocation, and try to think whether there's an issue geometrically. Would anyone like to take a guess as to which carbocation is lower in energy? I see a lot of students typing B. Yep, that's exactly right. So if we think a little bit about this carbocation A, and we think a little bit about what's going on here. So this carbocation A it wants, in terms of like bonded atoms, it wants to be sp-like. But geometrically, if you try to get a perfectly sp-like carbocation, if you try to get a true sp geometry, you will end up creating a pretty large amount of ring strain. You'll end up creating a pretty large amount of ring strain. So sp geometry creates strain, leading to a less stable carbocation. So in essence, we want to place our carbocation into a p orbital so it can participate in hyperconjugation, right? That's where hyperconjugation can actually stabilize our carbocation. However, if we try to place this carbocation in a p orbital, this sp geometry would create an incredible amount of strain. So in turn, this carbocation is less stable because it's less readily able to participate in hyperconjugation. Does this idea make sense to everyone? Does this idea of strain impacting stability make sense? Any questions on this explanation? So we want to place our carbocation in a p orbital. So we want to have our carbocation in a p orbital, which would involve having a carbon that is sp hybridized. The problem with that is, in a cyclic system, you can't have a carbon that's perfectly straight without introducing an unfeasible amount of ring strain. So as a result, we end up in a situation where our carbocation cannot be placed as readily into a p orbital and is, as a result, less stabilized via hyperconjugation. You can also view it as, in order to have a geometry that would best accommodate our carbon substitution pattern, that would create an incredible amount of strain, which would destabilize our carbocation. So there are many ways of explaining this phenomena. I always just want you to keep in mind, when you see the pictures drawn, just go through and do a mental check to make sure the geometry actually is feasible for that hybridization and for that system. Okay, that one was just a little fun thinking exercise. Let's take a moment and let's take a look at the following problem. We're asked to say and make an explanation for which structure has the most stable carbocation. When you take Chem 113, I want you to just save this page in your notes for when you take Chem 113, because we're slowly developing a really important skill in terms of predicting reactivity. And to start off on this idea, I'd just like you to take a look at each structure, structure A and structure B, and I'd like you to tell me which structure has the most stable carbocation and what atoms have a partial positive charge in each structure. And to help everyone out on that, I'll put some numbers here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I'd like you to tell me which structure has the most stable carbocation, and for each structure, which atoms have a partial positive charge. So take a few moments to work on this problem. You may have to draw some resonance structures, and then we'll come together as a group to discuss in about 3 to 4 minutes. And if you've heard of the Friedel-Crafts reaction, this is the common analysis and common thought process that you use when predicting the products for Friedel-Crafts reactions. But for now, just tell me whether A or B has the most stable carbocation. Yep, I see a lot of people typing B, and that is exactly right. So if everyone notices, we have a ketone functionality. This ketone functionality is an electron withdrawing group, and we do not want to place our carbocation adjacent to this electron withdrawing group. So we've clearly established that B, because it places carbocation away, or as far away from as possible, and on atoms that are not adjacent to our electron withdrawing group, B is more stable. However, we can't just look at these structures as drawn and make this conclusion. You are correct in noting that B is more stable and lower in energy, but in order to be thorough, you need to draw some resonance structures. So let's start with A. Let's start with A, and let's draw each of the resonance structures associated with molecule A. So first things first, we're just going to move our carbocation around the ring. And this is the kind of analysis I'm expecting you to do on exams. You take okay, so we're just pushing our electron density and moving our carbocation around the ring. Okay, and now as we can clearly see, in A, we have a partial positive charge on atoms 1, 4, and 6, okay? And the main issue being is that we have our partial positive charge. We have our electron deficient atoms adjacent to an electron withdrawing group. That's why our carbocation A is less stable. Let's look at carbocation B. Let's look at carbocation B, and let's try and see whether our carbocation is more or less stable. So just like before, we're going to push our electron density around the ring. And this is important that you draw your resonance structures. The reason why I'm asking you to draw your resonance structures is there are cases where I will show you a resonance form or another way of placing and drawing our alkenes for a molecule. And you're going to need to be able to push your electron density around the ring and check to make sure where are my electron deficient atoms and are they adjacent to electron withdrawing groups. So now that we have both of our pictures drawn for A and B, I'd like you to tell me, in structure B, do we ever have our carbocation directly adjacent to our electron withdrawing group? In structure B, which we said is more stable, do we ever have our carbocation directly adjacent to our electron withdrawing group, directly adjacent to our ketone? Do we ever see that? Do we ever see a carbocation directly adjacent to our ketone? Yes or no? No. There we go. Exactly right. But what's really important is you can't just look at the first two structures I give you and stop there. You really have to go through and draw the resonance structures. That allows you to give a complete answer, and that allows you to give a thorough answer. Does that make sense to everyone? Does the point I'm trying to make sense? Okay. So always make sure you're drawing your resonance structures just to check. Perfect. This one is another variation. So with this idea in mind, I'd like you to try this kind of problem one more time, and I'd like you to tell me which structure has the most stable carbocation and which atoms have a positive charge in each structure. And to do this, you're going to need to draw resonance structures. So I'll give everyone about 3 to 4 minutes, and I'd like you to tell me whether A or B has the most stable carbocation. And again, the word Friedel-Crafts alkylation springs to mind. But for now, we're just analyzing some carbocations here. And one thing to spark some ideas here is to think about what this ether group represents. Is it donating or withdrawing? Does that ether group stabilize or destabilize a carbocation? So let's take about another minute and a half, and let's get a few more responses in the chat with that question in mind. So I see almost an even split between A and B. Let's get a few more. So to provide one piece of data, as we discussed, if we have an adjacent atom with a lone pair adjacent to a carbocation, we can stabilize that carbocation via donation, right? So with that piece of information in mind, would anyone like to revise their response? Would anyone like to revise their response? So I see an even mix between A and B, but I see a lot more A's popping up now. Let's talk about this. So first things first, we are going to draw some resonance structures. So let's start with structure A. This time I'm not going to give the answer away right away. I'm going to make everyone have to observe all the resonance structures, and then we'll be able to draw our conclusions. Okay, so here's one of our resonance structures. Okay, here's another resonance structure. And here's the final resonance structure. Oops, I forgot the isopropyl group. Okay, so in structure A, is our carbocation stabilized or destabilized by our ether? Is our carbocation stabilized or destabilized? Is this ether donating or withdrawing? So I see a lot of people typing stabilized. That's exactly correct. This ether is a donor. It's an adjacent atom to a carbocation with a lone pair. Okay, let's now compare, let's now compare to structure B. So let's draw all of the resonance forms for structure B. Okay, so we kick our lone pair to stabilize our carbocation. Well, more correctly, delocalize our carbocation. Okay, one more resonance structure. Now, of course, presuming these resonance structures are equal contributors, which it's reasonable to say they're reasonably equal contributors, which structure, which carbocation is more stabilized and more delocalized via resonance, A or B? Which carbocation is more stabilized via resonance, A or B? A, exactly right. And we can essentially boil it down to the fact that in structure A, our carbocation is adjacent to our donor. In structure B, our carbocation is not adjacent to the resonance donor. So we are not able to stabilize our carbocation B via resonance as readily as carbocation A. Does this make sense to everyone? Does this idea make sense? Any questions on this idea? The only thing that I changed between these two examples is we went from a resonance donor, we went from a resonance withdrawer in the previous example to, in this example, a resonance donor. So just keep that in mind when assessing carbocation stability. Any questions before we move on to another example? Yes, it's more stable adjacent to a pi donor. That is perfectly correct. And it's less stable when it's adjacent to a withdrawing group. Yep, exactly right. But the thing I'm really trying to impress on all of you, draw all of the resonance structures, look at the resonance structures, see which molecule, which carbocation has the most delocalized and most stabilized carbocation, and then draw your conclusion. You always need to draw out the resonance structures to make a full informed decision. Okay, so let's do some more examples. And since we're discussing polar reactions, it's important that we review this idea of anion stability. And I'd like you to see the chapter 2 notes on anion stability. So everyone remembers this from our discussion of acids and bases, and we'll just discuss in order of importance. First and foremost, charge effects. So the larger the positive charge, the more acidic our species is. Okay, that's not as relevant for anion stability as the next discussion, which is atom electronegativity and atomic size. So anions are more stable on large electronegative atoms. That's why hydrofluoric acid is more acidic. However, atomic size has a larger effect on anion stability. So anions are stable on large atoms. Okay. We see resonance effects once again. So anions are stabilized via resonance. And the reason why we're talking about anion stability in the context of pKa values is that pKa values give you a tool to essentially qualitatively assess anion stability. The more acidic your species, the more stable that conjugate base anion, okay? So that's why, for example, the propyl alcohol derived anion or the propoxide anion is less stable than, for example, an acetate anion. The acetate anion stabilized via resonance. That's why this carboxylic acid has a lower pKa. So you can use pKa values as sort of a cheat sheet to guesstimate and estimate the relative stability of anions for the most part. So electronegative groups adjacent to acidic protons increase the proton acidity by stabilizing the conjugate base anion. So anions are stabilized via inductive effects. Oops, this one, cross this out and draw the correct structure. Sometimes the structure drawing program gets a little too adventurous. Okay, in terms of orbital effects, anions are more stable if the lone pair electrons are in a lower energy orbital. So in general, the more S character we have, the more stabilized our anion is. So an SP is most stable, followed by SP2, followed by SP3. The last major feature for anion stability has to do with sterics. So the less steric congestion around the anion, the more stable the anion. So that's why, as you notice, as we go from primary to secondary to tertiary, the tertiary anion, or the anion adjacent to a tertiary carbon, is sterically hindered. And as a result, less stable. And that has to do with solvent effects, which primarily occurs when we have protic solvents or solvents that can participate in either hydrogen bonding, dipole-dipole, or other stabilizing interactions with our anion. So this is review from our acid-base discussion. So what we're next going to do is we're going to talk about the fundamental aspects of chemical reactions and how we can measure and describe chemical reactions. So this is going to be a bit of a review of Chem 102 and a little bit from Chem 101. And what we're going to do is we're going to start to develop the tools to predict reaction products and assess the relative rates of chemical reactions. So to start off on this idea, let's talk about reaction enthalpy. So breaking bonds costs energy, forming bonds releases energy. Wonderful. So exothermic reactions, which produce heat, form stronger bonds in the product. So it forms low energy bonds that are stronger in the product than in the reactant. Exothermic reactions release energy. Endothermic reactions break stronger bonds than they make, and they require energy. So one key process that often occurs in chemical reactions is the making and breaking of bonds. And the bond dissociation energies, which we've seen before when we talked a little bit about radical formation, describes the amount of energy required to break a given bond to produce two radical fragments when the molecule is in the gas phase. So this gives us an idea of the energy associated with homolytic bond cleavage. So it's the energy associated with breaking a bond where our electron density is going to be distributed evenly to both atoms. So this is homolytic, where one electron is distributed to each of our atoms in the bond. Okay? So we can use these bond dissociation energies to estimate the amount of energy required to break a bond, roughly. And the energy formed when the energy released when a bond is formed. Bonds are stable. Okay. So we can use our bond dissociation energies to calculate the enthalpy of reaction. So quite simply, the enthalpy of reaction is the bond dissociation enthalpy for our bonds broken minus the bond dissociation enthalpy of our bonds formed. So to give you an example, we can calculate the approximate enthalpy of reaction for the combustion of methane. So if we draw out our Lewis structures for this, we're going to need to get a sense of what bonds we're making and breaking. And to do that, we need to understand what structures we're dealing with. So here's methane. Here's methane. Okay, we have two oxygen molecules. Okay. We have carbon dioxide. Okay. And we have two water molecules. Okay. Oops, one moment. Okay. So let's just do a tally. Let's just do a tally. So everything on the left-hand side, let's look at our bonds broken. Let's look at our bonds broken. So what bonds are we breaking here? So in methane, what bonds are we breaking in methane, fundamentally? CH, yep. And how many? 4, exactly right. What about in oxygen? What bonds are we breaking? What bonds are we breaking in oxygen? An OO, exactly right. So we're breaking 2 oxygen-oxygen bonds. Okay, what bonds are we forming? What bonds are we forming? CO, exactly right. And how many of those bonds are we forming? How many carbon-oxygen double bonds? 2. Okay, and how many OH bonds are we forming? Exactly right, exactly right. Perfect, perfect. Okay, so all we have to do now is we're taking the bond dissociation enthalpy for our bonds broken minus the bonds formed. If you use Hess's law, you can prove that you can use the radical bond dissociation enthalpy even if we're describing a polar process. You can check your Chem 102 text for that. So let's just plug in some values. So for our CH, we have 4 times 414 kilojoules. For our OO, we have 2 times 498 kilojoules. Minus, then for our carbon oxygen double bonds, we have 799 times 2. And for our OH, we have 464 times 4. And if we punch this into our calculator, we get the enthalpy of reaction is, give me one moment, I'm going to enter it into my calculator right now. And if someone has a calculator handy, I know for organic, you often don't have the calculator right in front of you, but we still want to calculate this just to show how this works, because it's a wonderful way of estimating reaction enthalpy. Now, combustion is obviously exothermic, and this gives us an enthalpy of negative 802 kilojoules of reaction enthalpy. Yep, perfect. So this is how you can use a bond dissociation energy table to estimate reaction enthalpy. So we can clearly see that this reaction is exothermic and it releases heat. Okay, this is boilerplate 102 calculations. Let's now expand on this, and now we're going to really delve deep and talk a little bit about enthalpy effects. So enthalpy effects. So reactions can be quote unquote driven to completion by a favorable reaction enthalpy. So common features of reactions favored by enthalpy. So enthalpy isn't the only driving factor for reactions, but it can certainly make certain reactions favorable. So for reactions that are favored by enthalpy, replacement of weak pi bonds with strong sigma bonds is a key feature that drives many reactions forward. For example, we call this a reaction an addition reaction, and it's driven by the fact you're generating relatively stronger bonds than the bonds you start with, okay? So think of it as like one feature that makes a reaction favorable, okay? The other feature that makes reactions favored by enthalpy, and you'll see this a lot, is this idea of the formation of a strong sigma or pi bond, such as silicon fluoride, silicon oxygen, or phosphorus oxygen. So I like to call these quote unquote thermodynamic sinks. And essentially these are super low energy species that can help drive reactions to completion. So Wittig reactions are often driven by formation of this very strong phosphorus oxygen double bond. So this delta H is less than 0. This is typically an exothermic reaction and can run away if you aren't careful. Okay, so these are ideas of how reactions can be favored via enthalpy. What we're now going to talk about is the other side of the coin in terms of understanding and what makes reactions favorable, and it's this idea of entropy. Okay? So entropy, as we discussed in 102, or as you've seen in 102, is a measure of the disorder present in a system. Now, a little bit more tangible definition is entropy fundamentally is measuring the number of microscopic configurations and microstates a system can occupy. And to demonstrate examples of low versus high entropy system, let's look at an example that we've seen a ton. So cyclic versus acyclic systems. So acyclic systems are relatively flexible, and they have a greater number of accessible conformations. And so we'd expect acyclic systems to be higher in entropy. Okay? Does this idea make sense to everyone? Does this idea of entropy, when we put it in a little bit more tangible terms, make sense? It's this idea of possible states that a system can occupy. High entropy systems can occupy a wide number, potentially, of possible states. Okay. When we think about physical states, gases are generally higher in entropy than solids or liquids. So for example, nitrogen gas is higher in entropy than liquid diazomethane, for example. And that's essentially because if you look at your gas or your gas sample is constantly in motion, and each of the gas particles itself can have a variety of different configurations and arrangements in 3D space. Well, if we think about a liquid and the liquid particles, the liquids have much less freedom of motion. They can certainly move about and bump into each other, but there's far less possible states and far less possible locations the liquid can occupy. So that's why gases are typically higher in entropy. Okay, the reason why we're talking about this, the real reason why I'm bringing this up is that there are a few factors in reactions that can increase entropy. So these are factors or aspects of reactions that are favored via entropy. So factors in reaction that increase entropy and are favored by entropy. So in general, the entropy of our universe is increasing. Favorable processes generally increase entropy. And the main way that you see this in chemical reactions in this course are the generation of multiple products. So if we generate more molecules, we are increasing the entropy of our overall system. So for example, in these elimination reactions, even though we are breaking relatively strong bonds and forming a weaker bond, we go from one molecule to two molecules. And as a result, our entropy increases. Does this make sense so far? Does this look familiar from 102? This idea of multiple products increasing entropy? Okay, the second major way that a reaction can be favored via entropy is if it generates gaseous products. So generation of gaseous products is also a wonderful way to drive reactions forward. So this carbon dioxide gas, in addition to the fact that this reaction goes from one molecule to two molecules, we have a bonus. Plus, we're also generating a gas, which is generally a higher entropy species. So as a result from this reaction, our entropy increases. There are additional benefits towards generating a gas in that you generally don't see equilibration or reverse reaction. But in general, for a reaction kicking off a gas such as carbon dioxide, nitrogen gas is a big one. Anytime your reaction is kicking off a gas, it's usually a pretty favorable process via entropy. Okay. And I just want you to think about these. These are things to consider when you look at a reaction and you're designing reaction conditions. What makes reactions favorable via entropy and enthalpy? Now, for those of you who've been paying attention, you may have noticed that entropy and enthalpy effects don't always necessarily agree with each other. So when we put together the enthalpy and entropy effects, we come up with this overall tool to describe reaction favorability that's known as Gibbs free energy. So delta G is delta H minus T delta S. So Gibbs free energy controls the ratio of products to reactants, and delta G represents the change in Gibbs free energy between the products and the reactants. So one thing I want you to immediately notice is that Gibbs energy is temperature dependent, okay? So as the temperature increases, the entropy term has a greater effect, right? As our temperature gets larger, this T delta S also gets larger. Okay. So at high temperatures, reactions that have a positive delta S that are favored by it, that increase entropy, become more favored. So at higher temperatures, this entropy term plays a bigger role. At high temperatures, reactions that have negative delta S value and decrease entropy become less favored, okay? So the main thing I want you to take away, as we increase our temperature, this entropy term has a greater sway on our chemical reaction reactant to product ratio, on our Gibbs free energy of our reaction. Okay, so let's look at an example. This is all nice in theory. How does this actually pan out? So let's look at a classic case where we're looking at the effects of heating on substitution and elimination reactions, okay? So, as we'll learn later on in this class, there are two possible reaction pathways when we have a nucleophile. Either we can have substitution or elimination, okay? What's observed classically, if we run this reaction and we just change our temperature, as the temperature of reaction increases, more elimination products are observed. And this is true for almost every elimination reaction that you'll come across. So our job is to explain this phenomena just from a fundamental perspective. We're just going to look at our reactants, products, we're going to look at the Gibbs energy of our reaction. We're going to try to rationalize this observation. That's the whole point of learning about all these ideas of enthalpy, entropy, Gibbs energy. We can begin to rationalize the products of chemical reactions and the behavior of chemical reactions. Okay, so let's think a little bit. How will the entropy term, or delta S term, differ comparing a substitution versus elimination reaction? Okay, so in a substitution reaction, we have two molecules reacting to generate two molecules. Okay, for an elimination reaction, we have two molecules reacting to generate three molecules. So if we compare substitution or elimination, which reaction is favored via entropy? Which reaction is producing more molecules? Exactly right, elimination. Yeah, so elimination is favored via entropy. Okay, so the delta S is greater than 0. Okay, so if delta G is equal to delta H minus T delta S, so as the temperature increases, the Gibbs energy of the elimination reaction decreases substantially, and as a result, elimination becomes more favored at higher temperatures. So, from this very fundamental perspective, we're able to conclude then we should run our elimination reactions at high temperatures, and our substitution reactions, we probably should keep our temperatures pretty low. Does this run through make a little bit of sense to help highlight the importance of understanding enthalpy and entropy and the idea of how temperature affects the entropy term? Does this make sense to everyone? I thought it's always a fun example, since when people are starting in graduate school to pick their own reaction conditions and they try to run a substitution reaction at high temperature and wonder why they see so much elimination product. If you think about things from a fundamental perspective, it can guide your your understanding and design of reactions. And that's the whole point of this chapter. Okay. So the Gibbs energy of reaction is related to the reaction equilibrium constant, which we call K equilibrium. And reviewing from 102, the equilibrium constant is the ratio of the product and reactant concentrations at equilibrium, accounting for stoichiometry. Okay? So for reactions that are product favored, we call these exergonic. So like, you know how we say exothermic, thermal, temperature, heat. Exergonic is energy. And the reason why we use this terminology is some reactions can make light, and those would still be classified as exergonic processes. They're releasing energy, okay? So the delta G is less than 0, and our K equilibrium is greater than 1. For reactions that are reactant favored, our delta G is greater than 0, and our K equilibrium is less than 1, okay? However, and this is a really important point, to look at which products are favored, we must look at the transition state and the activation Gibbs energy, or the Gibbs energy of activation. Okay? So the reactant and product energies can help us inform and explain equilibrium amounts of reactant and product. It can help us explain the position of equilibrium, but the activation Gibbs energy can help us explain selectivity. And this is our next focus. So we'll introduce this idea and then continue on with this idea next session. So let's talk about a brief introduction to the Gibbs energy of activation and transition states. Have you seen the idea of transition states and activation energies before in 102? Just to get a sense of where everyone's at. Okay. So the highest energy point in a reaction step is called the transition state. Okay. So this is the highest energy point. Okay. And each step is viewed as the transition from reactants to a product or an equal or an intermediate. So this would be one step. Okay? So the energy needed to go from the reactant to the transition state is known as our activation energy. Okay? So this gap here from our reactant to our transition state is the activation energy. Notice how the activation energy is different than the Gibbs energy of our reaction, okay? Okay, so in this case, in this reaction, we are looking at step number 1. So this entire process, we're looking at step 1, which is where we're going from our alkene to our carbocation. So all we're looking at is step 1. And we're viewing and we're thinking about the transition state for step 1. Does this make sense to everyone so far? Does this seem familiar so far? Now, don't fixate too much on the exact reaction we're focusing on. Just focus on understanding the 3 portions of the graph: the reactants, products, activation energy, and transition state. Okay. Now, there's a critical concept in chemistry, is this idea that reactions are reversible, and the reverse reaction can proceed through the same intermediate and the same transition state. Although the activation energy for the reverse reaction will be different. So to showcase what I mean, let's suppose for a moment, and we're going to do this in blue. Let's suppose we want to go in reverse. Let's suppose we want to go from product to reactant, right? So then, if we look at our delta G activation for our reverse reaction, is our activation energy the same or different for our reverse reaction? Is it the same or different? Let's compare the activation energy in purple, which is going from reactant to product. That's our forward. Is the same or different than our reverse reaction? It's different. And this informs how we can use these activation energies to also describe the position of equilibrium as well. We won't delve into that in too much detail into this class, but the key idea I want you to understand is that the forward and reverse reactions can have different activation energies, and depending on the activation energy, that determines the favorability and relative amount of reactant to product and the relative amounts of each of your reaction products, if possible. Okay? So we're slowly starting to piece together, and we're going to use this idea of activation energy and transition states to help explain the products and the ratio of products generated from our reaction. So we're going to stop here at 6:50 today, and we will resume our lecture on Wednesday, and we'll also lecture a fair amount in laboratory, just so that way we get through this next conceptual block. Is everyone comfortable so far? Does everyone understand what we've presented so far? Any questions before we close out today?